So today we shall discuss stochastic chemical reactions in microdomain. So this is really an application of the narrow escape theory that we have discussed in previous classes. So let me explain what are we going to see today and how we are going to analyze this. Suppose you have a micro container which can be a piece of a cell. So this is a piece of a cell. On the surface of the cell, so let's call this domain omega, and you have d omega, which is the boundary, and you have at specific location, specific spot, you have a substrate, and those are binding domains. So those are the binding domains. And so what happens is that suppose at time t equals 0, at any moment of time, some molecules are injected. For example, this can be the injection through a channel or any type of device through which molecules, ion, can go through. So let me put in blue the molecules. And so suppose the molecules, they move by Brownian motion or any type of motion. And then once they hit a specific site, they can form a bond. And so we are interested in, so we have, let's say at time t equals 0, m moving molecules, and suppose we have n binding sites. So here's the question that we would like to answer is, now if we look at the time t positive, what is the number of ms site, that is of bound sites, mn molecule at time t? So how shall we answer this question? And so this is interesting to get a model of this, especially when we want to study microdomains where experimental access is very difficult. So you can now imagine another situation where instead of having a closed domain, you have here a domain through which again you have a channel or any kind of mechanism by which molecule goes in, and you have here binding sites. So those are the binding sites. And the question we'll be interested in is now, what's the probability that you have a number of n sites, let's say equals to k. K can be 1, 2, 7, a given number, let's say n0 number of bounds. Because molecule can just go, so let me draw them in blue, they can just move and miss the target, and then they are extruded from the domain. Or some of them can go and can bind. An additional feature is that binding can be reversible. Can be reversible. Alright, so we have to also account for this. So in that case the situation is different. So we have case 1 here, where we have seen that molecule stay in the domain, and case 2, where molecule can eventually leave the domain. So what are the classical framework to study this process? So the very classical one is the chemical reaction in solution, where you have molecules M that can bind to the substrate S, and this is measured by the rate Kf. Kf is a forward binding rate, which depends basically on the global property of the domain, which account for the global geometry. the distribution of substrate and the diffusion coefficient. And basically, for example, in the Smoluchowski limit, we will see that we can give an expression for Kf as a function of, let me write it now, it depends when you have an isolated site and you ask what is the rate at which a diffusing molecule enter into a sphere of radius a. This is 4 pi a. D is the diffusion coefficient, and if there is an external concentration, this is multiplied by this concentration. So this is the Smoluchowski rate that we'll discuss later on. And then when the product MS is formed, it can dissociate. And this is measured by the backward rate, which we have seen in previous class, that the backward rate is exactly 1 over the mean first passage time for a molecule to dissociate from a potential well. Right, so you have the potential well here, and this is the potential, let's say, of molecule S as a function of the distance, and this is to measure the rate at which you reach here the maximum, so the particle is free again. And you have basically an energy barrier to overcome, which we have discussed previously. And so the limitation of this approach, so this is a classical rate of chemical reaction which disregards the geometry actually. There is no, the geometry is really homogenized. So there is no, when I meant here geometry means I wanted to suggest this, right? That you have to find a target. But it doesn't account, for example, if you have a domain with a specific shape for the shape of the domain. So this is the limitation. The second limitation is the fact that this is the mean equation for the mean number, so you cannot calculate any fluctuations. So no fluctuations can be computed. All right, so then another approach is needed. But what is interesting here is that still you can use this in solution, and you just need 2 rates to calculate everything. Now, a significant step was made in the 50s, in 1952 or 50, I think 1952, by Alan Turing, who proposed a set of chemical reaction. Actually, it's the paper is more deep than that, because he proposed at that time the concept of morphogen to understand how cells can be patterned and form regions. One interesting aspect is that for chemical reaction, in to include the space dependency, you can look at the diffusion equation for the concentration of molecule M. So here you have the diffusion coefficient, and the first equation represents the evolution of the concentration of M, which can diffuse. So this is the first term here, diffusion, and here is the reaction term that we have seen before. It's the same when everything is homogenized, except now that Kf here represents the rate of going through the binding, which doesn't account for the diffusion here. It can be modulated by the probability. So this is modulated now. Kf is or represent, I would write, is modulated by the probability of forming of binding, of forming a bond. And then you have the reciprocal reaction, that when you have a product SM formed, it can dissociate, and this is this second reaction. So this is 1 and this is 2. And again, this is for the mean, so this equation does not account for any fluctuations. And it's very hard to solve. Basically, today we know only to solve them numerically, and it's for very simplistic geometry. So the geometry is still very hard. So those are the limitation. The geometry is still very hard to take into account, and basically there are only numerical solutions. Really, the solving them analytically remains a challenge. So, all right. So now, what we are going to see today is how to apply what we have discussed about the narrow escape time to look at the discrete version. So you have a domain, you have the binding sites, you have, so those are the receptor S, which are located here, and you have M molecules that can move. So what we know is that if we have, let me draw it in blue, if we have a moving molecules M, moving by Brownian motion, because the sites here are small, that is the aspect ratio of this over the total domain is small, you can approximate that we can use that the time to reach the to reach a small hole is actually well approximated as Poissonian, which is 1 minus exponential lambda t, and the rate lambda is exactly 1 over the mean first passage time. And as we have seen, this does not depend really on the position of the particle m, but really it's independent of the initial position of the initial position, which will allow us to coarse grain the geometry here. So we are going to reduce the geometry of the domain omega by the rate lambda. Alright, so this is the basis of writing a Markov chain for the number of bound molecules. And indeed, this is what we are going to do now. And so this approach, as we're going to see, will allow us to derive the mean and the variance of bound molecule. So for this, suppose you write a Markov chain for the number of bound sites, that is the number of sites that contain the M molecules, and we want this to look at what happened between time t and t plus delta t when you start with already k bounds, and we would like to find an equation for this probability that the number of bound molecule at time t equals k. So for this we need to write a Markov chain. So how do you make a transition from k, let's say, to k plus 1 or from k minus 1 to k? What are the rates here for those transitions? And then once we will write those rates and understand what they are, we will be able to write the master equation. So let's write it this way. The probability that the number of SM molecules equals k at time t plus delta t. This is equal to the probability that SM equals k at time t multiplied by the transition. It's the transition that nothing happened, so it's 1 minus, and we will write it later on, that something happened. So this is the transition rate, transition, basically to characterize the phenomena that nothing happened. Transition rate for the event that nothing happens, right? So now let's write that something happened, and then we will use this to correct and to write what we need to needs to be written here. So plus the probability that there were previously k minus 1 molecule at time t. So then we need to see that during time delta t, something, the number of sites here increased by 1. So let me draw here a picture. So if we have exactly k minus 1 bound molecules, bound sites, so if initially there are n bound n moving molecules, so if k minus 1 here are bound, it means that it remains n minus k minus 1 molecules. And if there is a total of S0 substrate, how many free sites we have? So the number of free sites is exactly S0 minus k minus 1. This is the number of free sites. Alright, so now to make a transition from k minus 1 to k, it means that we need to have 1 molecules, 1 out of n minus k minus 1 that comes and arrive to a free site. So the rate is delta t divided by 2, or let's say this is the mean first passage time. And now we need to take one of these n minus k minus 1 molecules, multiply by the number of free sites, which is S0 minus k minus 1. Right? Now, the other possibility is that we started with k plus 1 molecules, and during time t plus delta t, one of this molecule has to leave in order to have a transition to k. So we need to choose now one of them. So it's 1 out of k plus 1 that needs to have a transition, so to be unbound, which is called with a constant k minus 1, which is the backward rate. This is backward rate, k minus 1 multiplied by delta t. So now we are ready to complete and look at what happened when we start with k and nothing happened. So this is 1 minus something happened. So this is 1 minus delta t divided by tau n minus k multiplied by S0 minus k minus delta t k, and then we have to multiply by k minus 1. Right, so this represents the probability nothing happened, there is no detachment, and here nothing arrived. Alright, and so this is exactly the derivation of the Markov. This is exactly the Markov equation for this transition rate. Right, so we can now rewrite this equation in the form of a system of equation. The way to do it is to move this term on the other side and to divide by delta t and send delta t to 0. Right, so this we'll do it now. So we can write, so again, I haven't looked at the extremities for k equals 0, but if we use what we have done previously, we get pk dot, which is the limit of pk t plus delta t minus pk of t, and we divide by delta t and send delta t to 0. And this is by definition, this is going to be m minus k, s minus k, with a minus pk, so there is here plus k minus 1, so there is, of course, I write it lambda, where lambda is 1 over time, plus k minus 1 multiplied by k, pk, and now we have the other term, plus k plus 1, pk plus 1, and here there was the term k minus 1, plus lambda m minus k plus 1, s minus k plus 1, multiply by pk minus 1. Alright, so now we have to be careful. So for example, for k equals 0, this term here does not exist, right? So we have to rewrite the equation and be careful. So we just get p of 0 equals minus lambda m s multiply by p0 plus k minus 1 p1, right? So this represents this is what you get from here. And of course, so suppose we're in the case where m is bigger than s, so the maximum is, of course, we cannot have more bound than the number of substrate s, so this is for the total number of molecules. Then you get an equation for ps, which is minus k minus 1 s ps plus lambda m minus s plus 1 ps minus 1. And finally, we need a normalization condition, because the probability has to be normalized. We need to have one state, the particles or the ensemble should be in one state, so sum of pk for any moment of time t has to be equals to 1 for k here equal 0 to s. And this defined fully the solution for these equations, what if we know how to solve them. All right, so I'll break here for the first part, and in the second part I'm going to discuss the steady state solution. Right, so in a minute we'll discuss now how to find the steady state solution. Steady state solutions.